Structural analysis to chapter 8, deflections using energy methods. So we want to solve an example in beams with the energy methods. If you remember, we have already solved two simple supports. So we have a pin at support A, and we have a roller in at B. And the distributed load of W is uniformly distributed over the span of B. So uh, if you just look at the equation of the load, that's W of X, that's the mass and also the concept. So if you integrate the load for once, it just gives you the shear in terms of mass and in terms of the concept both. And if you integrate the shear, it just gives you the moment. Area under shear is the moment, and also area under shear from the concept is also moment. And area under is nothing but just integration of your shear to get the moment. And if you just integrate the moment once more, it just gives you angle of bending, which is theta from 0 to LMD. And also, if you have four consecutive integration from load, you can reach to maximum deflection. We want to calculate maximum deflection. Definitely, symmetry, it happens at the center of the beam, as you can see. And if you remember, we already mechanics of material, we already calculated in chapter 12, which I will provide you with the link to that video if you want to refresh your memory with that. And we can easily get the deflection from the load or so if we want to calculate the deflection, maximum deflection, which is at the center due to uniformly distributed, if we cut the beam by somewhere by the length of x and loop the moment equation, whatever it is, and integrate it twice, it just theta, and the second integration brings you to delta. I didn't provide it here, but I will provide you with the link if you want to review it. And also you can, that's our first solution. You can also solve it. That was solution 1. Previous method, it was integration method. Solution 2 based off moment area theorem. If you use the second one, if you draw the shear, draw the moment, and calculate the tangential of A with respect to C, that's M over EI area under M over I times the distance to the first point. So times X bar. Just if you do the math, it just gives you the deflection of center of our shape, which is the maximum deflection due to symmetry of our structure. But these two approaches were something like in mechanics of solids. But if you want to solve it, the structural analysis method can also calculate it. For example, want to calculate a maximum deflection at C and also theta at A by the help of virtual board method, which is all solution 3, which is a virtual method which you're going to do today. So if we have a distributed load, uniformly distributed over the span of a L over a two simple support beam, definitely half of the weight goes for RA. So if this is W, that's the intensity times the length of the beam, it just turns to WL. And half of that goes for RA due to symmetry, or WL over 2 just goes to second support at B as well. We just cut the beam through by a length of X, and we just cut it by this amount of length, and definitely you can have RA, which is WL over 2. It just simply place from the top here, and also MX, there is a moment there. If we replace the distributed load by a concentrated load at the center, it just goes by W times X, and it stands with the half at the center, so that's X over 2 from X. If we just develop the moment about X goes 0, we have Mx in counterclockwise, that's a positive one, arbitrary direction of counterclockwise, that's positive Mx plus a Wx times X over 2, that's a half of Wx squared, minus the reaction, which is WL over 2 times the distance of X, and that's a counterclockwise, so that's a negative a half of WLX equal to 0. And if you write the moment equation based off that, it just simply gives you the equation of moment mx is equal to this term. As soon as you have the moment equation, and that's definitely due to real moment, because we just calculate the moment equation based off what we have on the beam. The second part, so if we want to calculate the deflection at something like any point, for example, point C in this beam, which is the delta at the center, if we just locate a 1 kilonewton virtual work at there, and we can easily observe the effect of that. Because our deflection is due to moment, we're just interested in virtual moment, which is the small m. So as soon as we have it, we can replace 1 here, a unit load at the center, and then cut the section in by the length of X. And if you calculate the reactions by this force, it just due to symmetry, either of RA and RB goes by half of that load, which is 1K, just goes by 1/2, and half A and B evenly distributed. And if we want to calculate the summation of moment about X goes 0, it just gives us small m, which is the virtual moment. Mx is equal a half of X. We just plot these two moments in the equation for 1 times delta CV is equal to 2 times m times capital M over EI dx. And just 2, it just comes from the 2 side of these two. If you just go by L over to double it, because it's a part of that. And a real moment is mx, and virtual moment is small mx times A is equal to this term. And if you just replace m with this m and capital M with the real moments and plug them in the equation, just integrate it, it just gives you these two terms, multiply them by each other, then integrate them and replace the limit of your integration. It just gives you 10 over 8 times 8 times 12 in the denominator, which is almost 0.013 WL to the force over EI. And if you get the problem and the solution, and based off what we had in mechanics of solids, again the solution 1 and 2, which I will provide you with them, it simply says if you have a simply support handling distributed load of W, delta at the center, delta max is equal to 5 WL to the force over 84 EI. Just divide 5 by 384 EI, you can get almost the same numeric value. So if these two are the same, we get the same answer from virtual work with the integration and moment area method, which is the solution 1, solution 2, and solution from structural analysis can get the same amount of deflection. Let's put it into a numeric value problem. So if you solve the problem with in a parametric form, it's easily by replacing the numeric value you can get the answer. So just assume the length of our simply supported is 8 meters and distributed load of W is 8 Newton over meters. We are interested to calculate delta max at C. If you do so by just replacing this equation and 5 WL to the force over 384 EI, or the other number, I think 0.30 something, work with the exact digit number, which is the result of this division. They are identical to each other. Then 5 times W is 8, length is 8 to the force over 384. EI is not provided, so it just gives us 426.67 meter cube downward over EI. And if you want to know how the unit works, it just gives you net meter cubed. It just directly from our calculation replaced in the numerator. In denominator, we have modulus of elasticity, which is G unit over meter squared in SI unit times I, which is a 112 base cube height. That's unit of meter 4 to the force, whatever you are. If you are in SI, that's meter. So you can get M to the M, M1. That's just something based off meter, and you can also report that by meters, because that should be a small number. If your EI is also provided, if not, just use the parametric form. Solve more problem. Thank you.